Okay, this unit we are going to work more with compounding interest, except that we're now going to be applying the knowledge to annuities. So first let's talk about what an annuity is. Basically, it's a series of equal payments at regular intervals. So for instance, if you have a 3-year loan and you pay $100 every month to pay it off, that's an annuity. Okay, there's the payment, or in the last unit we made payment equals 0 because we were looking at just time value of money and looking at compound interest on one specific amount or two specific amounts. Now we're actually looking at future value or present value, but of a series of payments. Okay, so that's where the payment comes in. N is the number of payments in the annuity, so it's very similar to how much was compounding interest, but in this case we're now saying how many payments are there. So then the meaning of N is very similar, but it changes because now we have a payment. If there's no payment involved, then N is the compoundings per year times the number of years. Now that we have payments, then N is the number of payments per year times the term in years. Okay, so we just have to be careful about how we use the N. So just take note of this, okay? The payment intervals, the time in between successive payments, or are we paying monthly or are we paying quarterly? And an ordinary annuity is, and that's what we're going to start with, is payments are made at the end. So you take out a loan today, your first payment back is at the end of the month or the end of the quarter. Okay, you don't pay an amount up front. We're going to talk about those type of annuities as well. But right now we're focusing on payments made at the end of the interval. And the term of the annuity is the total time from the beginning of the first payment to the end of the last payment. Okay, so if it's a 3-year annuity, a 5-year annuity, things like that. So this is what an annuity looks like. You have your day 0, the day you take out your loan, or your day that you loan money out, and the payments come, every whatever the interval is. So if it's monthly, so presume, for an example, this is monthly. So at the end of every month, up until the very last day, the very last payment, you have the same payment, the same amount of money. Okay. Now remember, time value money means that the payment, if it was $100 today and $100 5 years from now, okay, they actually have different values in terms of today's dollar value. Okay, but we'll address that in a few moments. Okay, so I just want to also talk about the types of annuity. So we talked about an ordinary annuity being that the payment is at the end. Okay, so and we have two different types of ordinary annuities. Simple annuities, in other words, the payment per year matches the compounding frequency per year. So if it's 5% compounded monthly, but you're also paying monthly, that's an ordinary simple annuity. An ordinary general annuity is when they're not the same. So you might be paying monthly, but your interest might be compounding quarterly. Okay, so we did that already with the when we did compounding interest. Okay, where sometimes they didn't match, and how to enter that into your calculator. Annuities due is basically it's the similar, but your payments are now made at the beginning of the month. So see how in this example the payments are at the end. Your payment would actually start with the first day you have your loan, or the first day you loan out money, and then it would continue to the day, the month, or the quarter, or whatever before your final. So you're paying at the beginning of the month. It's kind of like prepaying. You're paying at the beginning of the month to cover the month's due. Okay, and again, you have a simple and a general annuity due, and that depends on if your payments match your compounding. Okay, is your payment per year equal your compounding, then it's a simple annuity due. General, it's when they're not equal. Okay, so remember the words general. The words general imply that the PY is not equal to CY, and simple means that they are. Okay, and you can also look at, if it's annuity due, it means that it's due right away. So you're paying it ahead of time at the beginning of the period. Okay, so those are some key words to look at to help you remember which is which. So again, just like we did future value and present value of simple interest and compound interest, we're going to do future value of an ordinary simple annuity. Okay, we're going to start with the ordinary simple annuity. So at the payment at the end, ordinary meaning the payment per year matches the compounding per year. And then in 10.3, we'll look at present value. Okay, so the difference here though is that we have payments made every single month or quarter. So the future value, to try and calculate the future value of every single one of those payments, if you have 60 payments, that's a lot of calculations, okay? Because that's bringing everything to the future value. So it's the sum of the future values of all those payments. So, it's used to determine the amount of principal plus interest at the end of a series of regular payments. Okay, that's usually the most common. So how at the end, if I borrowed $1,000, at the end, how much interest did I pay on that principal? Okay, and you can also use to determine a single payment at the end of the annuity that is economically equivalent to that annuity. So if for some reason I couldn't make my payments, my last 3 payments, you might have to figure out, okay, how much would I owe in one lump sum payment at the end of that? So let's look at an example to help you I think this will make it a little easier. So my first example, $1,000 is invested at the end of every 6 months for 2 years, and it earns 8% compounded semi-annually. So let's break this down first of all. So that's the end, so that makes it a simple annuity. Sorry, let me rephrase that. The end makes it an ordinary annuity, okay? And every 6 months, that is also compounded semi-annually or every 6 months, makes it a simple annuity. So going back to our original, so ordinary simple annuities, the simple implies that the payment interval is the same as the compounding frequency, and the fact that it's at the end, okay, makes it an ordinary annuity, not an annuity due. Okay, so that means I'm gonna go back to my pen here. PY is the same as CY, which is twice a year, okay, semi-annually, and it's 2 years, 2-year term. And it's the 8% compounded semi-annually. So over 2 years, okay, so there's 2 years, but you're paid every 6 months. So that means there's 4 intervals, okay. So the first way you could solve this, so we have to find out, okay, what if it's $1,000 invested at the end of every 6 months, okay, how much is it? What's the future value? I guess there's no question here, so we want to find the future value, okay, because right now that's what we're focusing on. So you can do what they call the brute force methods, and you say, okay, after interval 1, you pay 1,000. 2, which is the second, so 6 months. So this is 6 months. This is 6 months. Okay, you have 1,000, 1,000, 1,000, 1,000. So there's 4 payments over those 2 years, and you're trying to find the future value of every single one of them. Well, the final one's just 1,000, but then the third payment is 1,000 with 1 interval, so 1,000 times 1.04, because it's I is equal to 8 divided by 2, which is 4%. Okay, and at interval 2, that's two periods away of doing the future value, so 1,000 times 1.04 to the power 2, because we're using our future value equals present value times 1 plus I to the n. Okay, and then the first one, it's three vesting periods or 3 interest periods. So that's 1,000 times 1.04 to the power 3, and you add them all up, and you get so the value of that ordinary simple annuity is, future value is $4,246.46. So in other words, if you put away $1,000 twice a year for 2 years, with the interest rate of 8% compounded semi-annually, at the end you would have $4,246.46. Okay, so that's the long method. We could use the formula. Okay, it's much easier to use. Again, we have our payment, which is $1,000. So this is where this comes, because each payment, now you got to remember, you're taking the future value of that payment, however many periods in the future. Okay, I is the periodic rate, which we know how to from last unit. 8% divided by 2 equals 4%, and n is the number of periods in the term. So we're paying out twice a year. It's for 2 years, so that means there are 4 payment periods. Okay, and if we substitute in our values, okay, so we put in the 0.04 and 0.04 on the denominator, and we do our calculations, we end up with the exact same final answer. Okay. Third method is the calculator method. Okay, so using the calculator is quick and easy. You still have all your information. You have interest per year is 8%, n is 4, payments per year is 2, compounding per year is 2, present value is 0 because you haven't saved any money. You're just putting but now we're putting, and this is the big difference, is where we put in payment equals 0 in the last unit. Now we put in our $1,000. So we're putting out $1,000. So our payment's going out. So that's negative. And if you compute, okay, future value, you get $4,246.46. So by far the calculator, it's the fastest and the easiest. And I highly recommend it, because when it comes to the tests, especially as we get along with regards to some of the other things, it's just a lot more work using the formulas. Okay, because again, just like in last unit, if you're missing any one of these items, okay, you can calculate it as long as you plug in the information. Okay, so and sometimes your present value might be 0. So perhaps I say I have $1,000, or let's say $2,000 in the bank, and I'm going to start putting away an extra $1,000 every 6 months. You would just plug in $1,000 for the present value. Okay, and you would plug that in, and you'd compute your future value, and it would add that in. Okay, so I want you to read over this. We'll read it together, and then I want you to stop the video and then try it yourself. Okay, and then when I turn the video back on, I'll explain how to do this. So stop video now. Okay, Elga plans to invest $175 every month by purchasing units in a diversified equity mutual fund. Okay, if the fund generates an overall rate of 6% compounded monthly, so remember she's doing it every month and it's compounded monthly, okay, what will her holdings be after 8.25 years? Okay, so let's plug in our number. Let's figure out our numbers here. So we have payments. Okay, I'm going to write it. So 175 payment. Okay. We have N is 8.25 years, so 8.25. Okay, and it's monthly, so times 12. Okay, and you get 99. So that's our N. Oops. I'm going to write it the way I would plug it in. So 99 N. Okay. IY, we're told, is 6%. Compounded monthly, so compoundings per year is 12. Payments per year is 12. So we do 6 YY. And then you do second second IY, and then 12, enter. Okay, that gives you that enters your PY. All right, so second IY brings up PY, and you put 12 and then enter, and then you do the up arrow, and that brings you to CY, and then you do 12, enter, and then second, quit. Okay, so now you've entered your IY. Okay, you've entered your PY and CY. You've entered your N. You've entered your we have to do present value still. So 0, and then present value, because there's she hasn't invested anything at this point. You've done your payment already, so then you do compute future value. Okay, and then when you do that, you'll get $22,346.66. So investing $175 a month for 8.25 years, okay, at 6% compounded monthly. At the end of that 8.25 years, she'll have $22,346.66 saved. So again, let's try the next one. I want you to stop the video once I tell you to. Try it yourself, and then turn it back on to see if you get the right answer. Okay, so Marcus spends $60 per month on cigarettes. Suppose he quits smoking and invests the same amount at the end of each month for 20 years. If the invested money earns 7.5% compounded monthly, how much will Marcus accumulate after 20 years? So this is if you smoke, this is here's how much you could save if you stop smoking now. Okay, so take a pause, try it yourself, and then come back and see if you get the right answer. Okay, just reviewing what information we were given. We were told $60 per month, so that's our payment. 20 years, okay, times month, because it's per monthly, so 20 times 12 is 240. Our interest rate was 7.5% compounded monthly, so CY is 12. PY is also 12 because he's putting in $60 per month, starting out with 0, so present value is 0. Okay, compute future value, and you get $33,223.84. So that's pretty good, putting my $60 a month, but you'll end up with $33,000. That's a lot of savings. Okay, so let's move on to another example, because this one's a little bit more, it's not exact. I want to go through it with you. Herb has made contributions of $2,000 to his RRSP at the end of every 6 months for the past 8 years. The plan has earned 9.5% compounded semi-annually. He's just moved the funds to another plan that earns 8% compounded quarterly. He will now contribute $1,500 at the end of 3 months. What total amount will Herb have in the plan 7 years from now? Okay, so this is kind of similar to when when you put money in, you let it sit for 3 years, and then you take it out and put it in, you get a different interest rate for another 2 years. So it's the same kind of concept. He's put in, let's start. So he starts making $2,000 contributions, okay, for every 6 months for the past 8 years. So dot, and so this is 8 years. And then he gets 9.5% compounded semi-annually. And then he's going to now start putting in $1,500 every 3 months. So this interval is 6 months. And this interval is 3 months. Okay. And this is getting 8% compounded quarterly. Okay. And he's going to, 8 years, and then he plans to do that for another 7. Okay, so 7 years. So 2,000, 6 months, 9.5 semi-annually for 8 years, and then he moves it to a compounding 8% compounded quarterly, $1,500 at the end of 3 months. So what will he have in 7 years from now? Okay, so that's our question. So the biggest thing is once you sort of dissect the question, you can then take it, start looking at breaking it down. So we have two. So we have sort of two. Let's look at the first 8 years. So first 8 years. And then we'll look at this second 7. All right. So the first 8 years, we have payments of $2,000. Okay. N is 8 years times it's every 6 months, so that's 2 or 16. Interest per year is 9.5%. Compounding per year is 2. Payments per year is also 2. Present value in this case is 0. Okay, so I think that's all we needed, right? So now we can then compute the future value, and we get $46,365.73. So that's after the first 8 years. Okay, so we've taken $2,000 times 16. So when you look at it, 2,000 times 16 is $32,000, but you're also getting interest at 9.5%, compounded semi-annually. So when you add up all the interest and the adding on to each of those payments, okay, you end up with $46,365.73. So now we're going to look at the second 7 years. Okay, our payments are now $1,500. Okay, our N is 7 years times quarterly, which means it's 4 times a year. So that's 28. Interest per year is 8. Payments, which is equal to compounding per year, is quarterly, so that's 4. Okay. And in this case now, present value is not 0 because you're now taking the money that was at the end of this, at the end of that first one, which is this whole $46,365. So that's going to still get interest, right? Because you're taking everything from that plan and putting it into a new plan. So their present value becomes $46,365.73. Okay. And remember, when you're putting in these values, one will always come up positive, one will always be negative when it comes to present value, future value. So don't worry about that. You can leave that as positive for now. And then when you compute your future value, and you can use the formulas for these, there's nothing wrong with it, except that you have to then take, if you want to, okay, well, present value gives you $136,367. If you're going to use the formula, okay, you then have to take the future value of this amount, this present value. So we take $46,365.73 times, and we do the future value of that compounding, like so 1 plus, now I would be 8 divided by 4, which is 2%. Okay, 0.02 is 28 periods. Okay, so 1.02 to the power of 28. That gives you the future value of that lump sum amount. And then you use the annuity formula. So 1,500 times 1.02 to the power of 28 minus 1 all over 0.2. Okay, so that's the formula you would use. And then when you do all the multiplication, you'll end up with the same amount. So see how you can see how it's already taking longer if you're going to use the formula, because you have to then take the present value of that first amount and add it to the the future value of that lump sum amount, and then take the future value of the annuity and add them together. In this case, when you use the calculator, you plug in the numbers. As long as you put in that present value, it also accumulates that as well. So the calculator does it all for you. Again, you can use either method, but it is definitely faster, especially when it comes to later on when we start looking at more complicated questions. Okay, so the other thing we're going to look at is the present value of an ordinary simple annuity. So in other words, if somebody was to offer me, or I had a certain amount of money, and I wanted to, I guess, invest it and get, instead of, I'm going to get a lump sum amount for the next 20 years. How much would I have to have now? So sometimes what happens is people will, if you're retired and you want to make, I don't know, $5,000 a month, you can invest that in an annuity at a specific rate. So you need to know how much is that going to cost you now. So if I put in $100,000, how much of annuity would I get out of that? So this is kind of this is one of the ways you might use it. So it determines that market value of the annuity. Okay. It also determines a loan balance. So if you still owe a certain, or you want to, if you're paying, you've got so many payments left on a loan, and the lender wants to sell it to somebody else, they can figure out how much that's worth, that market value. Okay, so let's do some examples, and we're very similar to, except instead of finding future value, we're not going to find present value. So again, $1,000 repaid at the end of every 6 months for a 2-year term earns 8% compounded semi-annually. You'll notice this question is exactly the same as the one we did for future value, but now we're going to do the present value of that same ordinary simple annuity. Okay. Again, you can do the brute force method by finding out the present value of each of the payments. So, and using the present value formula. Okay, present value equals future value. Now they've used 1 plus I to the n. They've used the alternate form, which is 1 plus I to the negative n. Okay, they're both exactly the same. It's just a lot of people, it's easier to just put power, when you do a power, do negative n instead of n, and multiply by the future value. So you can do the future value of every single payment. Well, when there's only 4 payments, it's not that bad, but when there's 30, it takes you a long time. Okay, so it's tedious and time consuming. You can use the formula. Okay, so it's very similar to the future value formula, where you take the payment and in this case you multiply it, instead of by 1 plus I to the n minus 1, it's 1 minus 1 plus I to the negative n over I. So it's a very similar formula. Payment in this case is $1,000. The number of payments, 2 years, twice a year. So 2 times 2 is 4. And the periodic interest rate, which is 0.08 divided by 2, okay, which is 0.04, and you plug the numbers in, and you get a present value of $3,629.90. You notice the future value of that the exact same question, future value of that annuity was $4,246, but the present value is $3,629. Okay, that's called time value money, right? So, you're taking what are each of those payments worth at that interest rate. Or you can use your calculator. Again, we had n equals 4, IY there were 8%. PY is 2 because it's twice a year. It's paid twice a year, compounding. Your payment, you're paying $1,000, so put in payment negative 1,000. Future value, okay, is 0 because you're trying to find out what the current value is, and you compute, okay, present value, and you get the exact same number. Okay, so again, if same sort of thing. If your future value is not zero because maybe you want to have a lump sum payment out at the end of that annuity, you would just add that in, and it's considered a single cash flow. Then you find the present value of that that particular ending cash flow. Kind of similar to when we did the future value on the previous section. Okay, so again, I want you to try something. Try it yourself. And I want you, in this case, I want you to use the formula and use the financial calculator. So it's, again, getting you to practice doing both. The more you get used to using the calculator, the better it will be. An ordinary annuity consists of quarterly payments of $100 for 5.5 years. What was the annuity's present value, discounting it at 10% compounded quarterly? So quarterly payments, 10% compounded quarterly for 5.5 years. So determine your N, your I, your payments, that kind of etc. And then use the formula, and then use the financial calculator, and then and then come back and see if you got it right. So pause now and try it yourself. Okay, so we identify our information. So our payment is $100 for 5.5 years. So that makes, and it's a quarterly payment. So N equals 5.5 times 4, which is 22. Okay, our interest rate per year is 10%, compounded quarterly. So PY is 4, and IY is 10. Okay, and then so we plug and so calculate I, that's 10% divided by 4, which is 0.025 or 2.5%. And we take our present value formula, plug in the information, and we get 1,676.54 is our answer. And when we use the financial calculator, we plug in IY equals 10, N equals 22, payment is 100, do the plus minus key to make it a negative 100, future value is 0, CY and PY are both set to 4, and then you compute present value and you get the exact same answer. Okay, so let's try next one. A new loan at 9% compounded quarterly requires quarterly payments of $727.88 for 7 years. Rounding to the nearest dollar, what amount was borrowed? So again, try it yourself and then come back to the video and see the solution. Okay, we identified our information. Our interest rate is 9%, so IY is 9, or if you're using the formula, it's 9% divided by 4, which is 2.25%, or 0.225. Payment is $727.88. N is the 7 years times 4 payments per year, which is 28. And your compounding per year and your payments per year are both equal to 4. Okay, so if you plug in the information in the calculator or in your formula, you should end up with $15,000. The original loan was $15,000. Note that it tells you to round to the nearest dollar. Okay, so make sure when you don't leave it with any decimals, you round to the nearest dollar. Okay, so that's ends up with $15,000. Okay, some other applications of present value regarding is loan balance and market value of a loan. Okay, so recall that the original principal amount of a loan is equal to sum of the present value of all the payments. And the balance owed after a specific payment is the sum of all the present values of the remaining payments. So if you had a loan that was 3 years long, and after the first year you wanted to pay it all out, for instance, you can find out what the remaining balance is by adding the present values of all the remaining payments. So what payments are left. So if you were to sell the loan, you would look at all the present value of the remaining payments, and that the value of it, that's what you would, I guess, sell the loan at. Okay, so let's look at some examples. Manuel purchased a boat for $2,000 down, with the balance to be paid by 36 monthly payments of $224.58, including interest at 10% compounded monthly. What was the purchase price of the boat? So quite often you see this when you look at say for an example, if you do a lease, okay, you put so much down and you're gonna, well, maybe not a lease, but a loan from the bank for a car. Okay, you have a couple $1,000s to put down and you got to make the rest in payments. This is all really what a bank loan is for a car. Would be exactly like this. Okay, except in this case, Manuel's buying a boat. Okay, so what was the purchase price of the boat? So first one, so the purchase price is going to be equal to the down payment, right? Because that's today's dollars, plus the present value, okay, of the monthly payments. That's the annuity part. Okay, so to find the present value of the monthly payments, we have, let's see, we're paying 36 payments, so N is 36. The payment amount is $224.58. Okay. Interest is 10% compounded monthly, and the payments are made monthly. So when you compute the present value, enter that information in, compute PV. Oh, don't forget future value is 0 because you're paying it off. Okay, you compute PV and you end up with you get 6,960.01. Okay, that's how much the present value of the monthly payments is. So that's only this part right here. So the price of the boat was the $69.60, and I'm sure it's 01 plus the $2,000 down payment. So that's $89.60.01. Okay, and so that penny is basically, it was probably more like $89.60, but because of rounding and whatnot, it ends up being a 1. Okay, so what was the balance owed just after the 9th payment? Okay, so there are 36 payments, and after the 9th payment, that means there are 27 payments left. And we want to find out what the present value of that annuity is. So you still have the same payment, the same interest. So payment is still $224.58. Your IY is still 10. CY is still equal to PY, which is 12. Future value is 0. Except now we change N to 27. This is where the calculator really comes in. So instead of you can use the formula and you plug it in and use the formula, but what you can do is just change the N. So put change N to 27 and then recompute that present value. And you'll get 5409.83. So that's the beauty of the calculator. The information's there. When you make one change, like for instance, okay, what's the present value after how much is still owed on the boat after the first 9 payments? You just change the value of N and recompute present value, and you're done. You don't have to worry about formulas. Okay, so the next one I want you to try. So again, I'll read it out. Government of Canada bond will pay $50 at the end of every 6 months for the next 15 years, and an additional $1,000 lump sum payment at the end of the 15 years. What is the appropriate price to pay if you require a rate of return of 6.5% compounded semi-annually? Okay, so take a few minutes, try it, and come back and check your answer. Okay, so we have a payment of $50. Our future value is that lump sum payment of $1,000. N is 15 years times twice a year, which is 30. Your interest rate per year is 6.5. Compounding per year, CY compounding per year is equal to the payments per year, which is equal to 2, and compute present value, and you get 13, 32, 18. Now the thing you're going to want to notice right here is the future value. Okay, what we're talking about is payments that are going out at $50. So that was the one thing we did. We made sure that payment went in as a negative payment. Negative. And since the payments are going out, but also this future value is going out, that's basically a lump sum payment out, make sure you put in, make that negative as well. Okay, because that's not what it's, the value, that's what's going to be left, and that payment is also coming out. So think of it as like both of the payments monthly, and at the end, they're both coming out, so they should be the same sign, or they should be negative. Okay, so be careful about that. Otherwise, you won't get the right answer. Okay, so it's really important that you take note of that. Okay, so try the next, actually, no, we'll do the next one together. Okay, so what is the maximum price you should pay for a contract guaranteeing month-end payments of $500 for the next 12 years if you require a rate of return that's at least 8% compounded monthly for the first 5 years and at least 9% compounded monthly for the next 7 years? Okay, so this is kind of similar to the other one, but now we're actually looking at, okay, we need to pay for, we're looking for the present value. So the present value of this stream. Sorry about that. Not sure why it jumped there. So we're looking at finding out the present value today. So let's look at our stream so we can understand the question. So guaranteeing month-end payments for the next 12 years. Okay, so this is from 12 years. So the first 5, we're getting 8% compounded monthly. Okay, and then 9% compounded monthly for the remaining 7 years. So this is from 0 to 5, and then 5 to 12. So that's 7 years. So we're trying to find the present value. Okay, so that means we're actually trying to take all these payments and we're trying to find the present value of them. And that's a lot of work if you were to try and do them, I guess you call it the brute force method. But we have it's like we have almost like 2 different annuities. So for what we need to do is first find out the value of the second one. So let's find out what the value that's good. So what we're happening is we're taking a lump sum amount and we're changing it what the interest rate is. So let's first find out the present value at year 5. Okay, of the so we have $500 payments. Okay, 7 years. Okay, and they are month-end payments, so monthly. So 7 times 12 is 84. Okay, our interest per year is 9%. Compounded monthly, so CY is the same as the payments per year, which is 12. Okay, our future value is 0, and we're going to compute the present value. So if you put that in your calculator, make sure it's negative payments. Negative 500 payment, 84N, 9IY. Second IY gives you PY, which is 12. Enter, and then go up and do CY should automatically be entered to 12. So you'll notice your calculator, whatever you put in for PY will automatically be put in for CY. So once we get into having a different compounding versus payment, you'll have to make sure you change that. Second, quit. Future value 0, and compute present value. And you'll get 31,076.98. Okay, so that's the value at year 5. So we know that that stream of payments, the second stream of payments, okay, the present value of that stream of payments, because we found the present at that 5-year mark is the $31,076.98. Now we have to find out the present value of the stream of payments. Oops, can't spell. Payment stream plus, okay, the present value of this $31,076. Okay, so we have two different things. So you can use the formulas. So you can use the present value of the $31,076.98 plus the present value of that payment stream, or we can just we can use our calculator. So we have 5 years. Okay, again, these are monthly payments. Okay, so n equals 60. The IY is now 8%. Payments per year is still equal to the compounding per year, which is 12. Okay, and let's see, what else do we do? IY. Okay, the payments don't change, so you can just make sure that the payment still didn't accidentally get changed from negative 500. Okay, and the difference here now is the future value. Okay, so the future value that you're starting with is $31,076.98. Again, because this is money that's gone out, make sure you make that negative. You compute your new present value at the beginning of the entire stream, and you get $45,518.41. Okay, so the answer is, what maximum price should you pay to guarantee that that's the, it's the $500 a month and that's the return you're getting? This is the amount. You shouldn't pay any more than $45,518.41. And at the end of your 12 years, okay, you will have received 8% for the first 5 years and 9% on the second 7. Okay, so that's future value, present value. And then what we're going to do is on Thursday, we will do some practice questions so that you can make sure that you understand everything.